Right. So I hope everybody remembers this, right? Remember this notion of basis sets. Good. Okay. Let's use this technique. Remember this technique. Let's try to find this A and B. Let's try to find this such an A and such a B. Okay. So, well, first, which is the fundamental property of leaderless protocols? And it is this one, that the initial configuration for an input x plus y, we are thinking of an input as a number, right? We are thinking of protocols for predicates of the form x bigger than or equal to c. So the input is just a number. And the initial configuration for the sum of two numbers is the sum of the initial configurations for each of them, which is not true in the case with leaders, right? Because in the case with leaders, the initial configuration for this, oops, take it again, have to wait. The initial configurations for this would be x tokens in a place plus a constant number of helpers. And here you will have the same, so you have twice the number of helpers, okay? So that's the fundamental property that makes the case with leaders more complicated. Good. So we have this property that we are going to use a lot. So now, now imagine that you start with the smallest number, with the smallest input, which is 2, because otherwise nothing can happen, right? Let's start at 2. And then you know that if you start at 2, you are going to reach some strong consensus. This is now a configuration, right? The configuration, which is a strong consensus configuration that we call SC2. And this is going to belong to one of these finitely many sets. So it's going to be of the form B2 plus, and by the way, this is also what I wanted to tell you. Why isn't it working? Anyway, remember that an example for something like this, right? The idea is that B is going to be a configuration. For example, it could be this configuration in a protocol with 4 states, and S is a set of states. For example, in this case, it could be Q1, Q3, and then this denotes all the vectors of the form 3 and then something x1, 1. Okay, this is the set of all vectors of this form. Good. So then this SC2 is going to be of this form for some B2 and then S2. And what is IC of 3? In IC of 3, by monotonicity, you can take IC of 2 and go to SC of 2, and you still have 1 token in the initial state, right? And this, from this configuration, you can still go, you can always reach, wherever you are, you can still reach a strong consensus, right? So you can reach from here and SC3, which is going to be some B3 and so on, right? And you can continue like this. And what is important is that, you know, you can always go from here to there, and from there still reach a strong consensus, because you can reach a strong consensus wherever you are. Good. So then you can continue like this. And of course, as you can imagine, pigeonhole principle, we only have finitely many sets of this kind, right? So there is going to be one that appears infinitely often. And now we restrict our attention to that one that appears infinitely often. We forget about the inputs that do not go to that set, okay? Or where you do not, where these configurations reach another set. Okay, and then you focus your attention on those, and then eventually you are going to be, by Dixon's lemma, right? You are going to find an A that goes to some strong consensus SCA of this special set which appears infinitely often, BA plus NS, and you are going to reach another one where this configuration is larger than this one. Okay? Well, the idea is then that this is going to be your A, and this is your B, you take as the increment that you go from here to there. And why is this going to work? What we have to prove now is that A and A plus B and A plus 2B and A plus 3B, that from all those inputs, you always reach the same consensus, right? Well, definitely, yeah, and remember from here you go to some SCB, which is which is SCA plus C, and belongs to the same than this one because we are restricting our attention to those. Okay, so we are staying within the same set, and then we find an SCB which is bigger than or equal than this SCB. Okay, good. And this is by Dixon's lemma, and then we can now show that the protocol has the same input for every input of this form. The same output, sorry, for every input of this form. So how do you do that? Well, from IC of A plus B, you can, this is what we are given, right? This is the given. And now what happens if you take IC of A plus 2B? Well, you can keep 1B, and with the remaining A plus B, go here, right? So you will still have the B, right? And now, from the, let's see, from SCA plus ICB, you can still go to SCA plus C. So from SCA plus ICB, you can go to SCA plus C, so you can go to SCA plus 2C, right? But then if this FCA and SCA plus C both belong to the same, then this one also has to belong to the same. And you keep doing this, right? So you have that all these, for all these inputs, you reach the same basis set, but remember that the property of a basis set is that all its elements are configurations of the same kind of consensus. Okay, they are all thumbs up or all thumbs down. Good. Yeah. So I get 2 knots, and I need more knots. Good. Okay.
And we know that V will be a closed double exponential because this is number of strongly connected components.
Sorry?
We know that V will be a closed double exponential.
No. I mean, we are now. This is the warm-up exercise where our goal is to show this, right?
And no, you overlooked that you need SCA plus ICB goes to SCA plus C. This is the difficult part. So you need that the ICB goes to something that is, so that you still go to something that is strictly larger than.
Right.
So you need
So the idea is that here from A, you can find an A and then A plus B,
yes,
such that from A you go to SCA,
yes,
and from A plus B you go to SCA plus C, for some C.
yes, but the number of different strongly connected components, we say that's double exponential, yes? Or
yeah, but the problem is the plus C. So you need that IC of A plus B goes to something larger than IC of A goes to. So you need the two SCA and ACA and the SCB to be comparable in Dixon's order.
yes.
Yeah.
Not just go to the same component, but one
Not just
above the
go to
other.
the same component, but to something strictly larger.
A larger configuration, a strictly larger configuration, right?
Yes.
And then, which is the only warranty right now, or the easiest warranty you can think of for that, Dixon's lemma. But then, of course, you have the bounds for control sequences, how long you have to wait until you see the first configuration, which is larger than another one. That bound is Ackermannian. Okay, this gives you a first bound. But now we want something.
Yes, I have a question. So I'm wondering, is it really important to be leaderless in the proof? I think for leaders it's the same proof, no?
It is the same for leaders?
Yeah, I think so, yes. Because, okay, it's not true that ICX plus Y is ICX plus ICY, but it's true that ICX plus Y is ICX plus Y, and without...
yes.
so I think it works.
That could be the case that for this one is not important.
Yeah, because essentially what you do is you take the B, you use the fact that IC of A is lying around to pump B into the C. So this does also work with leaders, but it's slightly.
No, but the problem is that when you go from here to there, right?
Yes.
The helpers maybe are now you don't know where, and then there is no warranty that with this B and the helpers you don't know where you can do still something, right?
But you can
But you
choose.
still have reachable
Yes.
configuration, so you still have to be
but
able
you
to go to some
still
SCP.
can.
You can fix
right.
this.
I mean, all you need is to go to some SCP.
Yeah, here you don't
Yes,
care,
I
right?
think-
Yeah, I mean, also
No,
in
no,
your
but
paper, right?
no, but the problem is those could be the helpers could now be in a situation which will not be reachable. You know, from the you may be in a situation where
No, I mean, you're only fired.
no, you don't know whether with the helpers in this configuration you know nothing about, and B in the input,
No, but I mean,
who tells you that you can reach a stronger consensus? Maybe you cannot.
no, I mean, SCA plus B is reachable. I mean, you literally have IC of A plus B, and then arrows start to this. So it's definitely a reachable configuration.
Yes, it's a reachable one.
It should work.
But
Okay.
it should be not ICB, but IC0B, maybe, without
Yeah,
the
I guess
constructor.
IC0B.
Okay.
Yeah.
Okay. But anyway.
Okay.
And I mean, also in the paper, you even proved this with leaders, right? So you. so I remember, like in this paper, you had this result here: Ackermann with leaders, and the leaderless one was the dog.
Okay, but thank you for reminding me that we already did it. Good. So yes, we are done. Okay, but now the real thing.
Yes.
What was the control?
The
Say
control.
What's the control? Which
you
control?
have a control sequence with Dixon's lemma. How did you control things?
Right. No, I mean, it is the usual thing when you are dealing with population protocols, right? You know, well, first you know where you start from. The initial, you know how many tokens you have at the beginning. And then when you go from one configuration to the next, you know that you can only decrease 2 indices by 1 and you can only increase 2 indices by 1. So that gives you
The total
I
number
mean,
of.
and by the way, when I am writing Ackermann n here, don't take this seriously. This means something like some variant, some whatever, right? So don't.
So I think the easiest answer is your number of tokens never changes. So this
Yeah.
you have a very simple controlling function. That
No. But I mean, the number of tokens never changes. But now you are. But it is different for every input.
Yes, but it's controlled by the number of tokens in A
Yeah.
plus lambda.
Yeah.
times
So
the
if you
number of
want,
tokens.
a way of controlling is to say the number of tokens here in all these things is given by these numbers.
Yes.
They were just consecutive numbers.
So.
Sorry.
I think this is about the last slide, and they were just consecutive numbers. So the draw function is just +1.
Yeah. Here they are consecutive numbers.
Yes,
Right.
but-
Sorry. Okay.
Yes.
Yeah. So yeah. Thank you. So I should have pointed to this.
It's controlled by a linear function.
Anyway.
Yeah, actually, I have another.
Yeah. Right.
Because
You are trying to delay the hard one, right?
the reasonings you make so far, you were using VAS in some way, right? For looking at Rakoff, Lipton, and so
Yeah.
on. But in the VAS, you're not conservative. You can create new things. Whereas in your rules, you're always conservative. So
Yeah.
how
No, what happens is that you are comparing one single Petri net or VAS or whatever with an infinite family of conservative nets, right? And some things can be transferred, some things cannot. And you are all the time playing that game. So it's not the same thing, but it's very similar. So I don't know what else can I tell you about it.
it's maybe like a conservative VAS, but initially you can create the initial amount.
That's a way of looking at it, yeah? That's a way of looking at it. Good. Okay. So the real thing. So now we want to find a different technique for A and B, for finding this A and B, which gives us a better one. Right? And then we are going to use this idea, which is the main idea that Philip Chernak had for doing this. So, you know, we want to find a condition such that when that condition holds, we have, again, something like this, which is just what we had right now in order to show that the A and B, for A plus lambda B, you always go to the same, you always deciding the same thing. So now the problem is to understand these conditions, right? The problem is to understand these two conditions. And let's do it. So the first idea is, well, from A, you can go to some intermediate D, which you have to think of a configuration where you have put lots of tokens everywhere, in all places where you can put a token. So you think at all the places where you can put at least one token, and then you imagine that by increasing the A, you then put a lot of tokens in all places where you can put tokens. Okay? So maybe let me do it a bit more carefully. So imagine that you have the Petri net representing your protocol. Here is your input place, and for an input for a given input, you are going to put that number of tokens here. So you can think of the same Petri net, but where you can put more and more and more and more tokens here. Then, starting when you put more and more tokens, then you think about which are the places where you can put one token. This is going to saturate at some point. At some point, it doesn't matter how many more you put, that's it, right? So, and of course, the others do not matter. You can never put a token there, so you just forget about it, right? So imagine now that these are the places where you can put tokens. And then, now we are going to think of this configuration. D is going to be a configuration where all places have lots of tokens. Okay? Good, that's the way to think about the D. So we want to imagine that from this A, we can reach at the configuration D with lots of tokens. We'll see how many. Then, what do we, in fact, the D is going to be like this. It has to put, and by the way, there is a typo there. It has to put at least this number of tokens in each place. And the question is, what is pi? Okay, and what is pi? So pi is the following. So what does this mean with the double arrow? With the double arrow, this means that, and pi is a paric vector, with the double arrow, this means if I were able to find a firing sequence with this paric vector, then that firing sequence would take me from here to there. Okay? And as you know, deciding if I give you a B, or if I give you this, and a pi, deciding whether you go from here to there is solving a linear system of equations. And as you know, finding whether there exists a pi is also a simpler problem. Okay? And moreover, you know further that if there exists a pi, there exists also a small pi. Okay? Because this is the problem of finding a solution to a Diophantine system of inequations. And there are theorems telling you that if there is a solution of exponential size. Okay? So basically, think about if I am able to find a pi for this, and if I am able to find a d here in the middle, whose size is exponential, and it also saturates the whole net, right? And such that from here I can go to some SCA, then I will be able to prove this. Then I will have that all these go into the same, or all are thumbs up, or all are thumbs up. And why is that? Well, it is actually, let's see, do I have a slide on it? Yeah, I have a slide explaining it. So what we want to prove is that if this holds, then I can go from here to there, right? And now the thing that I haven't underlined yet is the proof. Well, from here, this is the fundamental property, I can go here, right? This is just, in fact, I don't have to, it's just the same thing. I go in 0 steps there. Well, now, since I have this, right, I can go from here to there, right? And now the important thing is, you know, I have this paric vector pi, and I know that if I am able to find a firing sequence for this paric vector, then I will go from ICB to C. But since this puts so many tokens everywhere, anything, any pairing vector of this form, I can fire. Okay, so that's the idea. So this is the main step, which says that I can go from ICB to C, and this actually restores D. Maybe I have in the meantime I am moving around tokens, but in the end I have D again, so I can do it again and again and again. Okay, so I can go to D plus lambda C, and then I also have this part. But from D I can go to a C. So from here I can go
So
to
how do you know that from D plus lambda ICB you go to D plus lambda C? So how do you know that D will be restored? I don't know.
Well, because that's exactly what, what I know is that from D plus ICB with pi, I go to D plus C, right?
And this enabling anything.
I mean, if you have this, look at the semantics of this. If you have this, that you can go with the double arrow from ICB to C, then definitely you also have this, right?
Okay, maybe I didn't get the semantics of a pi arrow.
So this is just Z-bus reachability. Double arrow means Z-bus reachability, and D puts so many tokens everywhere that every Z-bus
above pi.
is
Okay,
actually executed.
okay.
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 So yeah, that's right. Call it set reachability. Okay. Would have been a better notation. Okay, so good. Okay, so now we have our proof technique, right? Our new proof technique. So now we know that we are done if we are able to find this. And of course, the point at which we have made progress is that we have replaced the single arrow by the double arrow. And that's easier to find, right? Good. So, but we still have to find it. We still have to find the A and B. Good. So the proof of the real thing is show that one can choose an A of double exponential size and a B such that these things hold, right? And if we are able to do this, then we are done. Okay, so the first idea. There are going to be two ideas.
And the D is large enough with respect to pi, right?
Well, that's already put in the condition. That's this condition. The D has to be...
Sorry.
Yeah, okay, good. I always like when people say there is an error somewhere because this means you got something, right? Even if you're wrong. Okay, so, well, the first idea is the following. If you have double exponential many tokens at the beginning, if A is double exponential, then it's definitely possible to achieve this for any exponential pi, right? And why is that? Well, let's first think about it. Why can't you achieve this for any exponential pi? Because the idea is that you are going to be able, in order to put one token, imagine I give you the Petri net and I ask you, how many tokens do you need in the initial place in order to put at least one token in this one? And you will say, well, double exponential is enough, right? So this means that with double exponential times the number of places, right? So you are going to be able to put one everywhere. Now you want to put exponentially many everywhere, multiply times exponential, but exponential gets subsumed by the double exponential, right? So it's enough. You can put exponentially many tokens anywhere. And now the second important point, and this is the point, this is Jerome's idea. So you can achieve even more. You can achieve more because you can even make sure that the A is much larger than the B, and exponentially larger. And again, why is it the case? Well, because you can choose A double exponential, and you know that the B's are double exponential at most as well, right? So again, by multiplying this double exponential with a single exponential, you can make sure that this is going to hold, right? That this is going to hold. And you have to visualize it in this way. You know, you have the configuration that you have reached here. right? And you have to think of that, of course, as this configuration needs some tokens are devoted to the B, and the rest is devoted to the rest, right? So the rest of the tokens there are many more than the ones for the B, right? It's only exponentially a small fraction of the tokens that is devoted to the B. The rest are here. Okay? Good. So we can achieve this, right? So keep this in mind. With double exponential number of tokens, I can make sure that this D puts exponentially many tokens anywhere. So I can find such a D for any exponential pi. And I can, at the same time, achieve that almost all tokens are in this part. This is much smaller than this part. Good. Okay. So the problem is, as you can see, if you compare this and the upper one, the problem is that we haven't got this condition yet. Okay? So we haven't got the condition that we can go to a C in S. We have achieved this from ICA, because we have this condition. From ICA, we find a row such that we can go to some ICA here. But what we need is not the configuration of the form B plus something in an S. This B has to be 0. The problem is the B is in the way, right? We have to achieve this, but without the B. So the B is what is actually in the way. So the question now is, can we get it with the B equals to 0, right? Or can we find this, let's say, intuitively with a B equals to 0? And this is where the second idea comes, okay? And the second idea, which is, this is, or if you want, is the second part of your Holmes idea. The first part is that the B is very small, is to use Potier's decomposition. And Potier's decomposition is this result telling you that the system of equations with m inequalities has a basis of solutions of a small size. Okay? What does it mean to be a basis? It means that every solution is a linear combination of the basis over the naturals. And what does it mean to be a small? A small means of exponential size in the number of constraints, basically. Right? That's what you mean. Exponential size in the number of constraints. Okay. So then, what we are going to do is, we know that we can achieve this. We know that we can find a row satisfying this. And now, this means that we have a solution of a system of linear inequality, because this is telling you only that there exists a solution to a certain system of linear inequalities, right? So we are going to start with that solution, and we are going to split it up into the basis. We are going to split it up into a sum of small solutions, and then we will see that one of these pieces has to have a 0 in the B. Okay, that's the idea. So let's go to the same. So we are going to decompose this solution that we already know we have into basis solutions. Okay. So, and the idea is, well, or the next step is the following. So we can choose definitely a heap of exponential size such that this holds, because remember, we can do this for any heap of exponential size. But the idea is that we can further require that all basis solutions have size at most heap. Because Potier's decomposition lemma tells us that the basis solutions have at most exponential size. So you can always choose the exponential in such a way that it satisfies both conditions at the same time. Okay? So of course there you have to manipulate the constants and all that, but all that can be done. So you can really achieve this. Good, and then once you have this, what happens? The idea is that you can decompose into basis pieces, And because of your choice of heap, those basis pieces, they are going to have size he. Okay? So what does it mean to have size? I am putting it in quotes there. What does it mean to have size he? It means that anything you see here has exponential size at most. Okay? And in particular, this EI has exponential size. Okay? And it is a decomposition into basis pieces. So we have the pieces look like this, but they have the property that when you add, you put them, imagine that you put them below each other, and then you take the sum here, and the sum there, and the sum there, and the sum there, right? And this is linearity. By linearity, I mean the idea of why this is a basis decomposition is that the sum of all this is going to give you A. The sum of all of this is going to give you the rho, and the sum of all the beta i's is going to give you the B, and the sum of the ci is going to give you this, right? Good. So now, how many pieces do we need? Well, for that we look at this. The sum of the AI's is A. And now we look at this, right? The beta i's, I mean, you need, each piece has size at most he. Okay? The sum of the pieces has to give us A. And we have this inequality. This means that we need at least the size of B plus 1 pieces. Okay? So we need at least the number of the size of B plus 1 pieces. But we also have that the sum of the beta i's has to be B. How many beta i's do we have? At least B plus size of B plus 1. Their sum has to be B. So this means at least one of the pieces, at least one of the beta i's has to be 0. And if at least one of the beta i's is 0, this means that we find an I, we have it here? Yeah. I find a specific I such that from here I go to there because the beta I is 0. So I go to there, and that's exactly what I need. Okay, because if you remember, this is what we are looking for. Something without a B, only the other part. Okay, so this is what we have achieved, and if you have made it to here, then we are done. Okay, this is the proof that you cannot go beyond double exponential. So this is the proof for leaderless protocols. And then now Jerome has an invited talk where he is going to explain the case with leaders, right? Good. The solution to the case for leaders is you cannot go beyond double exponential. Okay? And then there is the other, so every protocol, this is what Jerome proved, every protocol with leaders also satisfies the same property essentially, so in both cases leaders do not help. Then Philip Chernan proved that you can, prove what we have proved here for the case with leaders, that you can go to log-log. He proved it is possible to go to log-log without leaders. And I find this result amazing, and I very much hope that because it was rejected at some top conference for ridiculous reasons, in my opinion, and I hope that now it finally gets the recognition it deserves. Because notice the history is very nice, right? Lipton proves his result. You can weakly simulate counters, counter machines with counters bounded by double exponential an amount, right? And then Meyer and Meyer prove you can do it even if it is reversible. And now what Philip shows is you can do it even if you have no control about how many copies are running in parallel in a sense. Because the problem now is that you cannot guarantee that there is only one token in the states of the bus, right? So you can have it can happen that even if you have more than one, right, the machine should still somehow correctly simulate. This means you need a lot of machinery to achieve that. I mean, one thing that you can think of is, well, so this means this is as if there would be multiple control units acting on the same counters. Okay? Multiple copies of the same control acting on the same counters. And the problem, of course, you say, well, but if you have that, then everything is gone, right? There is nothing you can guarantee anymore. Well, no, you can. And the idea is, one of the ideas is these multiple copies, they can run a sort of leader election. If two copies find out that we are two copies running on this, then one of them can say, okay, I give up. Okay, that's one of the ideas. But another of the ideas is that you must be able to repair the damage that the other one did. I mean, you are doing your thing, and then you find out somebody else was acting on parallel, right? I mean, they are destroying everything I was doing. Okay, now we have found out that the other guy has retired, but the damage is done, right? How can I repair all this? Well, you can, okay? It makes things much, much slower, of course, but it's possible. I think it's an amazing thing. In particular, it means that, because the problem with leaders when you are thinking about chemical applications, leaders are very, very, very problematic because you have to guarantee their number. How do you ensure that a solution, if I think of the Erlenmeyer thing there, how do you ensure that that thing contains exactly one molecule of something, right? I mean, there is no way you're going to guarantee, right? So it is really necessary if you want to have, if you want to make the model a bit more realistic, you really need to make it leaderless. And the amazing thing is you can. And I find it is completely amazing, right? Because each agent, what is an agent story? I mean, it's not even storing one bit. You don't even have enough room to store one bit of the number, right? You don't have enough. You only have log C agents. So you cannot say, okay, each agent somehow is keeping track of a bit or something. No, you don't have enough agents for that. And still it works. So I find that truly amazing.
What is known about the set of all these C's?
Not much. I mean, there are infinitely many, and you will be able to find one every. So they are double exponentially spaced or something like that. Yeah. So I guess you can say something like you can find the k first within 2 to the k multiplied by something.
So they are uniformly distributed?
More or less, because the idea is that, they are given by the construction, right? The construction, I give you n states and then you construct the protocol. I give you n plus 1 or n plus 2 or so, you construct another one. And then you see which are the names they can deal with, right? So basically that's it. So they are going, you can say definitely something about the spacing.
Yeah, so one guarantee you have is that between a number and its square, there will be one number you can do it for.
Really? No.
Between a number and its square, you can, yeah.
Between any number and the square,
yeah,
starting from some point, right?
Starting from some point, yeah. For the first 100 numbers, it doesn't work. But after that, between a number and its square, you will find something. So, for example, between 100 and 10,000, there's some number you can do it for. Or between 10,000 and
okay.
like 1 million.
Okay, I believe that because of the double square.
Yeah, the idea is you do this repeated squaring construction, so you know that between every number.
Well, but I'm not sure if probably it's between. Okay, well, it doesn't matter.
Well, Philip told
between
me
a number and between 8 and 7 in a square or something like that. Right? I don't think it will be, but anyway, it doesn't matter. Yeah, that you're right. Yeah, very good. Actually, that's much better than the answer I gave. So the idea is you listen to me for the wrong answer and then you listen to Roland for the right answer. So this is the summary then. If we forget about leaders and non-leaders, because in the end it doesn't, now we know that it doesn't really make a difference, right? At least at a certain point of abstraction. Then for every C, there is a protocol with O of log C states. That's the very first one I gave you, and that works for every C. For every C, every protocol needs at least this log C to the 1/3 states. And for infinitely many C, there is a protocol with O of log C states. Okay, so that's the final picture. So the ratio between the microscopic and the macroscopic world is double exponential. Yeah.
But is it known that the best one can do is for infinitely many? Is it possible that this actually exists for every C?
For every C? No, for every C we saw. In fact, you can only make it for an exponentially small fraction of the numbers. Because of this idea that you don't have enough protocols.
Oh, I see.
That was this very simple idea that if you have n states, you can only produce exponentially many protocols, so you cannot have. Okay. Good. So, how much time do I have?
We start late, no? Because we make the room table. We can.
But
I mean,
because,
20
you know,
minutes,
one
maybe
possibility is
10,
if you are
10
tired, we can stop here. Another possibility is I tell you a little bit more about the same stuff. And another possibility is I tell you about an open problem in population protocols. How much time do you have to say?
So it depends. If we want to finish at 12, it's 10 minutes, or if we want later, it can be 20.
Then let me tell you, let me go for the last option, the open problem, because the nice thing is that I can do it by showing you movies. So this is a tool which, among other things, can simulate population protocols. So, for example, this is the first protocol we saw, the one with the pouches. The ninjas have pouches, right? So, and then instead of 4, let me say, okay, the ninjas want to know whether they are at least 10. So the states are going to be 0 to 10. And these are the ninjas in the same garden. But initially we are going to have, let's say, 13 ninjas, right? And they have to find out whether they are at least 10. And initially they all have 1 pebble in their pouches, and then you can now see them active. And you can see that some pouches get bigger, right? And eventually 1 pouch will have more than 10, and then everybody, they start telling other people, right? And that's it. Now they've reached the thing. Okay, let me do it again. But this time, let me do it with, let's say, 64 numbers. There is no special reason for the 64, but let me just take 120 million. So there are many more than 64, right? And then they start to play. And I was this is not what I wanted to do. I wanted to stop it at a point, and then I was too slow. So let me do it again with you. Let's see it again. And now the problem I have to stop it at the right moment.
Javier, we can slow it down.
Yeah, I know, but okay. Let me stop it there. So there are now. Remember, there are 110 ninjas, right? Many more than 64. Now what happens is that, the ninjas want to attack a castle. And the guys in the castle, they have sent a sniper to the garden. And the sniper is trying to kill ninjas, right? And of course, the goal of the sniper is to avoid that the ninjas attack. So he wants to make the protocol, even though there are enough ninjas, he wants to make them reach the wrong result. And the point is, the sniper only needs to kill 1 ninja. Because if the sniper now kills the 46, the one with 46, then the rest, imagine that they disappears, right? Then the rest, they are never going to reach consensus, even though they are very many, right? They are very many. So the problem is that this protocol is very fragile. It's not fault tolerant. One single fault can cause it to fail for a situation where it should still achieve the right protocol, right? The right result. So in fact, if you think about it, if the 64 is the bound, then by killing one single ninja, you can make the protocol fail for up to 127 ninjas. Because it could be the case that at some point it's 64 here, 63, 126, right? 63 and 63, so they haven't reached 64, and at that moment you kill one, right? So this protocol is very fragile. And now the question is, can you make the protocol robust? Is there any other protocol which is robust? And yes, there is one. So let me take something like 10.
Robust means by killing only one, yes? Or
Okay, well, let me 1 second. Robust is going to mean, what's going to mean? It means that if the ninjas have to decide whether they are at least 64. And there are 127, right, or 26. Then this means that the sniper is an adversary, right? The sniper can choose when to kill a ninja, right? But the idea is that the protocol will only fail if the sniper brings the number really below 64, okay? It cannot make them think that they are not 64 unless they are not 64. And this protocol achieves that. And it is very simple. The idea is you think, I haven't shown you think about it in this way. The ninjas imagine that they are in a building, okay? Where, with a number of floors. And the rule is very simple. They are initially all at the ground floor, at floor 1. And then, whenever two ninjas interact, if they discover that they are in the same floor, one of them goes one floor up. Okay, so the idea is that the ninjas hate company. They want to be in their own floor, right? Whenever they see, oh, two of us are in the floor, okay, one of us goes one floor up. Okay? Well, eventually, if you imagine that there are infinitely many floors, eventually the ninjas are going to be at most one in the floor. Okay? And now if you think, okay, they are more than 64, and there is at least one in every floor, then whenever if they start being more than 64, eventually one will reach the floor 64. Imagine now that that's the top floor. Okay, and then when a ninja reaches the top floor, then it starts bringing all the other ninjas up to the top floor. And eventually they are on the top floor, they know they are all 64, right?
Well, but if at that time the number of ninjas start to drop below.
Yes, okay, so the moment, that's the point, at the moment at which they have reached the consensus, at that point, if you kill ninjas, you will not change, they will not change the consensus anymore. They cannot, right? But, okay, that's something you cannot achieve anyway. That's a fundamental limitation of the population protocol model.
I mean, when this one ninja is starting to bring others, it's like it still requires some operations. Yes, so like he's meeting with the other, it's like, okay, 64, so now we are...
No, but imagine they are 67, right? Yes. And imagine one has reached the top floor, yes, and now the sniper kills that one. Then there are 66 left. And then another one will reach the top, because whenever there are at least 64, if they keep working, at least one reaches the top again. Because they always keep...
But the question is, if one reaches 64, and the killer kills 3 from the 4 from the bottom floor, he will, the one that reaches 64 will go back to...
What is true is that if the ninjas may have decided to attack, they have reached a strong consensus, and at that point the sniper kills many and brings them below 64, it's true that the ninjas will not know this, right? They will still, the remaining ninjas will still think they are more than 64. But that's a fundamental problem of the population protocol.
So you assume that the sniper cannot snipe you below 64 and should start above 64. Because if
Anyway.
the sniper could bring you from above 64 to below, your protocol would always be wrong, no matter what protocol you try.
Okay.
But now I only have 3 minutes, so before we continue this discussion, which is probably very interesting, let me tell you which is the problem. The problem is, I mean, ninjas cannot only decide whether they are at least 7. They, in fact, there is a population protocol, this is well known, for every predicate in Pressburger arithmetic. Okay? And this is exactly what the ninjas can do. So they cannot decide whether they are a prime number, because that's not in Pressburger arithmetic. They cannot decide whether the product of the number of blue and red ninjas is equal to the number of yellow ninjas initially. They cannot do that, but they can do anything in Pressburger. And now the question is there a robust protocol for every Pressburger predicate? And we don't know. What we do know is the following. So every protocol in Pressburger arithmetic can be expressed as a Boolean combination of thresholds and modulo protocols. So then the first question to ask is there a robust protocol for every threshold predicate? Sorry, Boolean combination of threshold and modulo predicates. The threshold predicates are linear combination greater than or equal to constant. The modulo predicates are linear combination equals or greater than or equal to something modulo something. Okay? So we do know that there are robust protocols for arbitrary threshold predicates. We know that there are robust protocols for arbitrary modulo predicates. But the constructions are not closed under composition. So we don't know what happens with the combinations.
So the
Okay.
composition doesn't preserve robustness.
Sorry?
The composition of protocols doesn't preserve robustness.
How do you prove that there is a protocol for every Pressburger predicate? The proof is done exactly like that.
Yeah.
You find protocols for threshold and modulo predicates, and then you find a construction that taking two protocols for two predicates gives you a protocol for their conjunction or for their disjunction. There are very simple way of doing that is basically the product construction of automata works. If you think for a second about it, and about for complementation, you just swap thumbs up and thumbs up, right? And that's it. That's the proof. But those constructions do not preserve robustness. Robustness is always defined, and the problem is, the intuition is that if you have imagine that you have a protocol for a predicate x less than or equal to 5, and you have another one for x bigger than or equal to 5. So the problem is that the disjunction is the true predicate. And the requirements for robustness of true are very strong, right? You have to be able to give the same result independently of how many ninjas. In each of the two predicates in isolation, you have to worry about fewer ninjas, right, so to speak. The sniper is not allowed, doesn't have much munition. For the disjunction, the sniper suddenly may have much more munition available, okay? And that's the problem. So I think it's a very interesting one, and yeah.
What is known about number of states needed for robust protocols?
Very good. We don't know. We have a conjecture that you need many more states if you want to make the protocol robust. In fact, if you think about the Tower protocol, has, how is it? No, in this case, no, that's not the problem. In this case, the Tower protocol doesn't have many more, right, than the other one.
Well, it's exponential in the binary.
Well, it depends. If you, right, imagine that you take the one I gave you, where in order to know whether they have reached this number, the one for the powers of 2, right? There, the number of states is logarithmic in the C, but this Tower protocol, the number is the C. The number of floors in the tower is C, not log of C, right? So this one has exponentially many more states than the other one, but this is the only one we know about that is robust. So probably the conjecture is that requiring robustness involves an exponential blow up in the number of states, right? But we don't have a proof.
Do you have any concrete Pressburger predicate for which you don't know a robust algorithm?
Yeah, which is the one, Roland?
Well, I mean, basically for any complicated
no, but
combination,
there is a specific one.
Yeah, there was one specific one.
Come here, Roland, come here, write it down.
So I actually prefer to draw this because, well, I'm a geometric guy. So we have x and y inputs, and then the first thing we take is we take everything below the diagonal. So this is y is less than or equal to x, y less than or equal to x, and then what we add is we add every fifth point directly above the diagonal.
Well, it's not important, it's every fifth.
Yeah, you could also take every but it doesn't matter. You take some kind of modulo, or you have y equals x plus 1, and what does it mean every fifth one? I guess x is congruent to say 1 module 5.
Right.
Because x is even will also
Yes.
work, right?
Yeah, x is even is not quite as easy. The problem is that now
You
at
always,
these points
always have to translate Roland's handwriting, right? So this is x is congruent to 1 modulo 5. Right?
Yeah, so well, the protocol will intuitively have a problem at these points here. Because why? So the path y less than or equal to x is only robust if you stay y less than or equal to x. So at this point, you give the sniper 0 points of ammunition. But for the disjunction, you give the sniper 1 point of ammunition, because if he snipes a y, then you stay in the y less than or equal to x region. And if he snipes an x, then you move into the other part of the Boolean combination, and the other protocol is now supposed to take over for you. And so this is why at these points here, fundamentally the product construction will give you very complicated, it will not work, because this protocol does not have to be robust at this point, because you would not be able to snipe x's. But this one and this one can only take over because you sniped something, otherwise you were not even accepted in the first place.
And now if you ask us which conjecture do we have, I conjecture that there is one, and Roland conjectures that is not the case. So we don't. I cannot give you anything. So we should split you into two groups. One tries to prove it. So let's take a poll. Yeah, let's take a poll. So out of your gut, who thinks every predicate has a robust protocol?
I can shoot.
Sorry?
I can shoot the ninjas.
You can shoot.
Now you run your protocol.
Yeah. Who is, so you are, who? And who doesn't? So it's kind of equal, right? Okay, interesting. Yeah. So we are optimistic.
I guess that's because you said I'm on the low side. And I think it's probably
okay, so yeah, that's it.
Thanks.
Okay, we have time for questions.
A bit more generally about the Fidelity protocol, does it make sense to talk about probabilistic specifications where you want a consensus to be reached, but you're allowing the consensus to either be yes with probability 0.7 and no with probability something else?
Yes, of course it would be interesting. And well, there is, okay, what definitely has been studied is protocols with a small probability of error.
Then you can fix it using another protocol.
Yeah, so the idea is that the wrong answer, the answer being the wrong one, and then instead of saying, well, it has to be with probability 1, say, okay, with probability at least 95 or so. And then, yeah, that may have an effect on the number of states. So if you relax that condition, then you may be able to have protocol. I mean, but we don't know. I don't have any results telling you, well, okay, imagine that you need a protocol for X greater than or equal to C, but you are happy with 99% probability, right? Whether then you can go beyond log, I don't know. It could be an interesting question, yeah. It could be an interesting question to ask. But you know, the problem is these things are then hard because, for example, if you allow a small probability of error, and okay, you have to be a bit careful about what I'm saying, but essentially it could be the case that you end up with a model that is Turing powerful. Yeah? And then so you can compute any predicate, and then of course things become much harder.
Yes.
Can you give us a sense of which semi-linear sets you can do with robust? You know how to do with robust protocols?
No, that's of course the one thing that we are trying to. I mean, when trying to prove that, that there is a robust protocol for every predicate, then you try to since we don't come forward, we don't make progress with disjunctions for conjunctions. We are trying to switch to the semi-linear to expressing the predicates by semi-linear sets, but we haven't made any progress, and Roland is very pessimistic. That doesn't bring anything.
So, for example, can you do
all linear sets, for example? So, no, not even that, right? Roland, we don't. Not even for linear, right? We don't have a proof that for every linear set there is a protocol. Not even.
No, because a linear set also has a modulo condition inside.
Right.
So and like even a linear set also has multiple thresholds, and already a conjunction for threshold we at the moment are not sure whether we can do.
and also it says one variable?
In one variable, we thought about it, and everything has a robust protocol.
Yeah, for one variable, yes. Which was the construction? I don't remember anymore.
So the reason is that there are so few predicates. It's like, so you can always write this, I'm congruent to something, modulo something, and I'm at least something.
I mean, yeah.
And
so there is a generic construction, maybe that helps, right? There is a generic construction which, if you know in advance how many bullets the ninja has, and that number is independent of the number of ninjas, right? So if you know that the snipers come with 5 bullets, okay, then you can construct robust protocols for any predicate. Okay, but the idea is you do not, the sniper has a lot of ammunition, right? It's unbounded ammunition, and can use, if there are more ninjas, it can also use more bullets. So that would be the, and also, but also then the next question comes, right? There is if you have only a fixed number of bullets, what happens with the states? Because the construction that achieves it blows up exponentially the number of states. So then the next question is, so you know, there is a lot, and I haven't started to talk about time, right? So you know, that's what I like about the population protocol model. Instead of talking about markings and firing sequences, you are talking about ninjas and snipers, and it's more fun. That's more fun.
Okay, thanks.
Good.